Welcome everyone to this afternoon's lecture. It's a special occasion. The winner of the CRM-Fields-PIMS prize this year is Professor Daniel Wise from Yale University, and we're very pleased that he's taken the time to come here. And as part of his cross-Canada tour, the requirement of the prize is, well, let's call it a condition of the prize, is that the prize winner should give a talk at each of the three institutes. I think you've been to PIMS already.
Right, but I haven't yet been invited.
Your home is
right.
At your home city.
Yeah.
Let me just say a few words about Professor Wise. He Princeton PhD in 1996, faculty positions at Berkeley and Cornell, before joining the Yale University in 2001, and he's a full professor for a number of years. Honors and distinctions, so Fellow of the Royal Society of Canada. From a mathematical point of view, fantastic work on part of the geometrization conjecture of three manifolds. So the Devlin Prize, shared with Yale in 2013, and an ICM speaker at the 2014. So foundational work in geometric topology, geometric group theory, very active PhD supervisor, as I've been hearing, and mentor of students. A masterful speaker, as I can attest myself in previous talks. So we're very pleased, delighted to have Professor Daniel Wise here this afternoon. He's going to talk to us, as you see, about the cubical route through understanding groups. So please.
Well, thank you very much, and thank you for your generous introduction. Let me get acquainted with the technology, or reacquainted. So, it's like that. This is my little joke of cubulating groups. So I like to cubulate groups. We'll talk about that in a moment. So here's a rough outline of what I'm going to speak about. I'm going to, and I have until it's 1 hour or 50 minutes? It's 1 hour, okay. So I'm going to tell you a kind of scheme for understanding, a little plan for understanding a group. It doesn't always work, so it works sometimes in some very interesting cases of interest. And I'm going to describe the steps, though I know most of you won't understand what I'm talking about, and then you will understand afterwards. So nevertheless, I think it's good to see what this plan is, what the steps of this plan are. So first of all, we want to find a bunch of codimension 1 subgroups. Okay, those are subgroups which are going to cut the group in half. Okay, and then from there we're going to get an action of the group on a cat0 cube complex. So that's a space built out of cubes. Okay, and if the subgroups which will cut the group in half are nice enough, then the group is going to act nicely on this cat0 cube complex. Oh, I even illustrated things over here. So here's the Cayley graph, right? And one of these codimension 1 subgroups is the red dots over there. And the cat0 cube complex that you're going to get is going to be dual to these codimension 1 subgroups, and the translates, the cosets, so to speak. Well, once you've obtained this cube complex, x tilde, the next thing to do is to find a finite index subgroup of your group. That's going to be G prime. Such that the quotient is very organized. And it's what we call a special cube complex. So this isn't quite, these two are not quite related to each other. But this might be the quotient, x tilde mod G, and then I pass to a finite covering space, that's going to be x tilde mod G prime. And this guy over here, it's a complex built out of cubes, which is very organized. And you'll see what I mean soon, right? You can't quite tell yet, but somehow it's in an interesting encoded way. It's related to this graph over here. And once you get to this special cube complex, what you find is that your group, or rather your finite index subgroup G prime, embeds in what's called a right-angled Artin group. Okay, and a right-angled Artin group, which we'll call a RAG, that's a very, very easy group. So here's it's a bunch of generators, and you just declare some of them to commute. And from there, you find that the finite index subgroup it turns out to be a very easy group. It's a subgroup of an easy group. I'm going to go through all of this now again in greater generality, but in detail rather, or some detail. But you see, it's just a few steps of some plan. Okay, so well, first of all, what's a cube complex? Okay, so an n cube is what you expect it to be. Or maybe my coordinates are not quite what you expect. Okay, here's a 3 cube over here. And as you can see, a cube has subcubes, right? That's what you would, I think, know what I mean. And a cube complex is just built from cubes by gluing them together along subcubes. So here's a cube complex right over here. Okay? The rule of the game with me, generally speaking, is that if you think you see a cube, it's a cube. Okay? And now, so we need to say, we know what a cube complex is. You just glue together a bunch of cubes. We need to say what it means for it to be non-positively curved. Okay, and the way that's going to be a definition which will be a local definition. So first of all, a flag complex is a simplicial complex with the property that a bunch of vertices span an n-simplex if and only if they are pairwise adjacent. Okay, so you're welcome to ignore that and just think about it this way. You draw a simplicial graph, right, meaning no loops or bigons. And then you add, whenever you have a simplicial graph, you just add a simplex whenever you see its one skeleton. Okay? And that's the way to think of a flag complex. You just take a simplicial graph, and then throw in all the missing, all the simplices that you think are there. Okay? So here are 2 examples of flag complexes, assuming that you've added these simplices. Now, the link of a 0 cube, inside of a cube complex, I'm looking at this 0 cube right over here, its link is the simplicial complex which corresponds to a kind of epsilon sphere around it. Okay? So, you put your eye at that 0 cube over here and you look outwards, and, a 3 cube which is attached which has a corner at that 0 cube is going to give you a 2 simplex. Your eye looking out into that 3 cube, you'll see a 2 simplex, right? And for a 2 cube, which is attached with a corner at that 0 cube, you'll have a 1 simplex, right? And you're just imagining all the different directions outwards. All right? So this is the link of a 0 cube. So here's a picture of the link of that 0 cube over there. Please stop me if you have any questions or if you think your friends have questions. So a cube complex is non-positively curved if the link of each 0 cube is a flag complex. Yeah, it's a kind of combinatorial version of a notion of curvature. Well, yeah, there kind of is, and I'll talk about that in a moment. Okay, but it is in fact, from my viewpoint, it should usually well, sometimes it's better to treat it combinatorially and sometimes more metrically, and you'll see in a moment. Okay, the answer to your question. So the motivation, I think, is pretty clear, right? So these are pictures of surfaces over here, and you recognize this zero cube right over here as kind of a positively curved 0 cube, right? Because that could have been a sphere, could have been part of a sphere, right? And over here, you know that's flat, and over here you've got negative curvature, right? And if you think about the links, right here, the link of this 0 cube is a 5 cycle, right? And here it's a 4 cycle. Here it's a 3 cycle, and that's problematic because it's not a flag complex. It's missing a 2 simplex, right? Because there's no 3 cube in that picture. Okay? This is a 2-dimensional picture. So that's the motivation. Although this is really a high-dimensional theory, cubes of any dimension are allowed. It's good to have in mind just the 2-dimensional case. Almost all understanding of this can be an intuition about it comes from 2 dimensions. So if your complex is 2-dimensional, then X is non-positively curved precisely if each link is a graph that has girth greater than or equal to 4. Okay? That then is, I think, quite simple. a graph, and most of my pictures are going to be pictures of two-dimensional square complexes, okay, two-dimensional cube complexes just built out of squares. So, of course, any graph is non-positively curved. Any surface, except, a sphere or projective plane, is homeomorphic to a non-positively curved square complex. Okay, that you're familiar with the torus, right? You glue the opposite sides of a square, and you get a non-positively curved square complex. But the same for higher genus surfaces as well. And here is an example. If you take two non-positively curved cube complexes and form their product, it's again non-positively curved. Okay, so you should be having it in mind. Two graphs. Take the product of two graphs. It's non-positively curved. So that's already a source of examples for you. All right. So I told you what a cube complex is, and even told you what a non-positively curved cube complex is. Now I want to tell you what a RAG is, what a right-angled Artin group is. So it's very simple. You take a simplicial graph, and let's call it gamma, and associated to that simplicial graph is a group presentation whose generators correspond to the vertices of the graph, and two generators commute if and only if those vertices are adjacent to each other. Okay, so let's look at three examples over here. So the RAG, the right-angled Artin group associated to this simplicial graph over here, it has three generators, and any two of them commute. So that's going to be Z cross Z cross Z, right? Here's a more interesting example. There are 5 vertices, right? This is a complete bipartite graph on 2 vertices and 3 vertices, right? So 5 vertices. Any 2 on the left are adjacent to any vertex on the left is adjacent to any vertex on the right. Okay, so this is going to be a group which is presented by 5 generators. The 2 generators on the left commute with the 3 generators on the right. So it's the product of 2 free groups. Okay, a free group of rank 2 times a free group of rank 3. Here's a little bit slightly stranger example. You have 4 generators. A commutes with B, B commutes with C, C commutes with D. And what I'll just tell you about this is that it turns out this group, I'm not going to bother writing down the presentation, you already know how to play this game. It's just the fundamental group of a 3-sphere minus this chain of 4 circles. So I'm using example because it's actually the fundamental group of a, excuse me? Okay, so what should I do? Do you want me to explain why these are isomorphic to each other? I won't. Okay. Give me another way out?
I don't know what array of options you have. That's true.
Okay, so, well, you have to compute a presentation of a sort of link complement, and you can pick it out from either a Vertinger presentation or a Dane presentation after you mess around with it. I think that maybe I'm not going to spend a lot of time on this, but I will do the following. So, right. So maybe I screwed this up. But I will do the following. I will tell you what some generators are. How these vertices correspond to elements in this in the fundamental group of this chain in this link complement. Will that satisfy you? Yeah. I mean, we need some way to let me out of this. Yeah. Okay. So what did you say? 4 points and 4 circles. So each generator over here, right, of this of the group presentation that's associated to this data is going to correspond to a circle that travels, from a base point and goes through one of these circles. Okay, so that's a rough idea, but it's pretty easy. Okay. Alrighty. Now, of course, I hope that you all prefer this way of describing the information, the RAG associated to some graph, instead of this way of describing the information, where you just take a bunch of generators and write down that some commute. Right? When I write a commutator, it's just saying that A and A times A prime is equal to A prime times A, saying that this is a relator. Okay, these are just, I haven't met anybody that prefers this way of writing it down, but I've heard that there were people that preferred that years ago. Okay. There's no relation between A and A prime. So, well, here's little a, and here's little A prime, and you see that A is the name of this vertex, and A prime is the name of that vertex. Those are generators of the group, and they're adjacent to each other, and so A and A prime commute with each other. Was that your question?
It looks like the symmetric generates at those values.
It's not symmetric because so there's no relation between. There's some symmetry to it, I guess, a little bit of bilateral symmetry, but C and A prime don't commute with each other, for instance, right? So you notice that there are some missing relations. Okay. Alrighty. Connecting back to cube complexes, to non-positively curved cube complexes, I wish to point out that the fundamental group, that any RAG is actually the fundamental group of a non-positively curved cube complex, people sometimes called a Salvetti complex. So it turns out to be quite easy. So for instance, here's a graph, right? It has 4 vertices and 4 edges. Okay, I just added one edge to this graph over here, right? And well, if you think about what the information is, what the data is for the presentation, right? I said, a bunch of generators and a bunch of relators. There's a so-called standard 2 complex of that presentation. It has a single 0 cell. It has a 1 cell for each generator. I've actually written, here's the 0 cell. There's a 1 cell for each generator, right? It's a labeled graph, right? And then I attach a 2 cell for each relator, right? A and B commute, so I attach the 2 cell A, B, A inverse, B inverse, and I attach a 2 cell B, C, B inverse, C inverse, and so forth. Okay? So far I've created a 2 complex, right? And notice that it's a 2 complex, which is actually a 2 complex built from squares. And finally, I can add a cube for the 3 pairwise commuting generators, right? And so you take a cube, right, which here it is. You look at it carefully, and you realize it's the way you would have built a 3 torus, right, by gluing together opposite sides, opposite faces of a 3 cube, and you kind of where to glue that on, right? You glue it onto the you see what the attaching map is. You see how the 2 cubes that are on the boundary of this 3 cube are glued on to the 2 cubes over here, just using the labeling. Okay. In general, this is the way the game goes. If you have a RAG, right, you have some simplicial graph. You just add a cube for every collection of pairwise commuting. You add an n cube in this fashion, in this manner, for every collection of pairwise commuting generators. Okay, that's I haven't explained it in detail, but you can recover it now. All right. I don't think I will. Okay, because well, it's kind of written over here. You just can ignore. You can ignore this. Ignore these 2 pieces of data because we're ignoring this blue edge over here. Okay, and what you could do, I suppose. So here I am pulling back to the example. Sorry, can control myself. What you can do is you can embed the yellow, the sort of 1 skeleton, and the yellow and the 3 yellowish squares. You can embed it inside of the complement of this chain of 4 circles, so that if you add in the point at infinity, right, then everything will deformation retract to that complex, which will be a spine for it. Okay? Okay, good. So, who's your friend, by the way? Okay, good. Huh? You think I shouldn't have given him that entry? There's always anytime you go to speak about your stuff, there's usually the local person who asks questions for everybody else. He's the hero of the audience and someone that the speaker hates. So, and it's okay. I mean, sometimes what I do is I ask people to just point them out right to begin with, but I think that will not be necessary, right? Let's continue. Okay, carry on. So it's good. It's good for that talk. Cat zero cube complexes. Whoa. So a cat zero cube complex is a simply connected non-positively curved cube complex. Okay, so what you do is you take a non-positively curved cube complex and then look at its universal cover. Okay, here's an example that you've seen before, right? A hyperbolic plane, except that we've kind of made it more, combinatorial, and we've cut it up into squares, 5 meeting at each vertex, right? You look at the link; it's simply connected, certainly, and you look at the link of a zero cube, and you see that it's a 5 cycle. It's good. Okay. Now, getting back to your question about why we're using the term non-positive curvature, any cat zero cube complex actually has a geodesic metric where the cubes are isometric to Euclidean cubes. Okay, and where this geodesic metric satisfies what's called the cat zero inequality, which was popularized by Gromov, and it says that if you take 3 points in X tilde, and you look at and you look at a geodesic triangle, meaning a triangle formed from geodesics joining these 3 points, then that geodesic triangle is at least as thin as a Euclidean triangle with the same side lengths. Okay, in the sense that if you take points on this geodesic triangle in X tilde, and you look at points in the same relative position in the Euclidean plane, right, in that triangle, in the comparison triangle in the Euclidean plane, then the distance between the points in your triangle in X tilde is less than or equal to the distance between the comparison points in the Euclidean plane. So these cat zero cube complexes have such a cat zero geodesic metric. Okay, and this is something that this comparison triangle condition is from Riemannian geometry, and it's a global condition, but also local condition. The X has a non-positively curved cube complex has a metric which is locally satisfies this property, and so I hope that satisfies. I hope that answers your question. Okay. Okay. So, in fact, the notion of cat zero cube complex was introduced by Gromov, just to give a source of examples of cat zero spaces outside of the manifold situation, outside of the Riemannian non-positively curved Riemannian manifold situation. But there's no way in the world that he anticipated that they would sort of slowly grow and take over a certain sector of the field that he was getting everybody all excited in. But he's a good guesser. Man is a good guesser. So, all right. I said that cat zero cube complexes are more of a combinatorial business than a metric business. So let's see what makes them tick and what makes them behave the way that they do. So a mid-cube in a cube is what you get when you restrict one of the coordinates to 0. So a 3 cube has 3 mid-cubes. You cut down the middle this way, or you cut down the middle this way, or you cut down the middle that way. Okay. The mid-cube of a 1 cube is just its barycenter. Okay. A hyperplane in a cat zero cube complex is a connected subspace which intersects any cube that it does intersect in an entire mid-cube of that cube. Okay. And what I want you to think about is, this mid-cube right over here, and try to imagine how it works, how that mid-cube extends outwards to become a whole hyperplane inside of this cat zero cube complex. You kind of see this mid-cube, and it intersects this 2 cube over here at a point, right? And then you have to intersect it in an entire mid-cube. And then you intersect the next 3 cube at a point, so you have to intersect it at an entire mid-cube, which is looks like a little 2 cube. And so and likewise, if you continue off in this direction, you see what's happening, right? So if you start somewhere, you have to continue, right? And so you're quickly convinced that if a point lies in a hyperplane, or if a mid-cube rather lies in a hyperplane, then it's going to lie in a unique hyperplane because it had to be a certain specific one. But in fact, every mid-cube does lie in a unique hyperplane. So there exists some hyperplane. What could go wrong is that as you're working your way out, you come back and you crash into yourself. But that can't happen because of the non-positive curvature. Okay, the non-positive curvature ensures that as you're working outwards, you're always going off in new, unseen, unvisited directions. Okay, each hyperplane separates the cat zero cube complex into two parts. Right, the part on you could see it has a kind of its neighborhood. It has a product neighborhood. You could see so you could see how it's separating it. And well, I would claim that it's the hyperplanes that give a cat zero cube complex its personality. So they generalize the role of edges in a tree. And in fact, cat zero cube complex are generalized trees. They're high dimensional trees from a certain viewpoint. Okay? So you can imagine here's one hyperplane inside of that cat zero cube complex. You can imagine all the others. They're what you might, they're likable things. Okay? And here in the Euclidean plane, right, there's vertical and horizontal hyperplanes. Okay. All right. So I'm going to quickly mention immersed hyperplanes, then I'll tell you to forget about them. So my goal now is to tell you what a special cube complex. Remember, I said that was an organized cube complex. Okay. The way in which it's organized is going to have to do with the way its hyperplanes behave. Okay, so any non-positive, any cube complex even has immersed hyperplanes. So you just kind of do the same thing that we were doing a moment ago. You start in a mid-cube, like this one over here, and then you work towards the neighboring cubes, and you keep pushing your way outwards, right, through mid-cubes, okay, and until you kind of come back again to where you started. And when you do this, you might crash into yourself and come in through a different mid-cube than you had entered a cube beforehand. Okay? So you might not get an embedded object. It might just be immersed inside. Okay? You see this red-green hyperplane comes back and crosses itself twice. Okay? So I'm now ready to define what a special cube complex is, and it is a strange definition. A cube complex, a non-positively curved cube complex, is special if its immersed hyperplanes have the following four properties. First of all, no hyperplane self-crosses. It doesn't come back and cross itself. Okay? So we don't have to worry about immersed hyperplanes anymore. Okay? They're actually hyperplanes in the way we defined them earlier. Second of all, each hyperplane has a product neighborhood. No hyperplane is two-sided. You don't have a Möbius strip, for example. Third of all, no hyperplane self-osculates. That means it doesn't come back and come close to itself like that again. So what do I mean? Technically, what it means is, so you have these two, the hyperplane, this red hyperplane is kind of dual to these one cubes, right? And what we require is that a hyperplane is not dual to two different one cubes that are adjacent to the same vertex. Okay, but you should just that picture is what you should think of. That doesn't happen. And lastly, this is the most complicated, is that no pair of hyperplanes interosculate. So that's a little bit hard to say what I mean over there. So that means you can't have two different hyperplanes that cross each other in one spot and then come back and osculate with each other in another spot. Okay, so all in all, this is the strange definition of a special cube complex. Okay, it was cooked up with Fredrik Haglund and myself. One example to bear in mind, and an easy example, is any subcomplex of the product of two graphs is special. So I mentioned that the product of two graphs is a non-positively curved cube complex. And actually, if you take a subcomplex of a product of two graphs, then that's going to be special. It's easy to check that these pathologies can't occur. Yes, please.
It would only be strange definition if there were other forms of functionable behavior that are allowed. I say that's not true. Maybe if you don't disallow these four things, maybe it's legally well behaved.
If you disallow these things, then it's completely well behaved. Well, I mean, it depends on what do you mean by completely well behaved?
Well, look, I would say that there's pathology and there's normal behavior.
You accept these as pathology. You accept these things that I'm excluding. You agree that these are pathologies?
Yeah.
We're on the same team then.
Okay.
So then I agree.
Okay.
I agree. So you don't, so it's I would say that the first two are certainly just saying that there's a little neighborhood, a cubical neighborhood, which is a product, right? The third one is saying, well, that if you think of it as a closed cubical neighborhood, it embeds, right? So these first three are really you can convince anybody to accept them as reasonable. The fourth one is a little bit more obscure. Okay? Okay. So.
If the hyperplane comes back and just touches, but on the opposite side, that's also disallowed.
In the third case, say that again, please. In this situation.
Right.
You're asking about this. Huh? That's a great question. I ducked it. Okay? Unsuccessfully. This is allowed. This is allowed. And it's because since hyperplanes are two-sided, you can sort of put a direction over here, and the hyperplane is dual to directed one cubes, and they don't have the same incoming vertex or the same outgoing vertex, and so that's actually allowed. Okay, so whenever you have this type of behavior, when you subdivide the cube complex, it goes away, and so we don't get hung up about it. And in fact, the way this theory works out, this is acceptable behavior. Okay, great. It's good that you caught that. So I try to mix up scolding questions and giving positive encouragement. Okay? Okay. So, all right. Well, it turns out the following thing holds, that X is special if and only if there's a local isometry from X to a Salvetti complex of a rag. Okay? So remember what that meant? It meant that there's a local isometry from the non-positively curved cube complex X to the non-positively curved cube complex, which is associated to a right-angled Artin group. And what that means from the viewpoint of the fundamental group is that the fundamental group of X pi1 injects in the fundamental group of this Salvetti complex, which means that if X is special, then its fundamental group is a subgroup of a rag. So we'll sometimes call a group special if it's the fundamental group of a special cube complex, because that being a special cube complex, it maps by a local isometry into the Salvetti complex of a rag, and like as in Riemannian geometry, local isometries between non-positively curved manifolds induce pi1 injections. Well, the same thing holds in this for these singular metric spaces. Local isometries between non-positively curved cube complexes induce pi1 injections. Okay, so what should you get from this is that we have this crazy, or maybe you like it, definition of a special cube complex, an organized cube complex, and being the fundamental group of one of these things is basically the same thing as being a subgroup of a rag. Okay? Now, I bravely attempted to draw a special cube complex. Okay, this actually is special. And to just give you, since maybe you're curious, to tell you, well, if you have a special cube complex, what rag is it actually going to be mapping to by a local isometry? What rag is it naturally associated to? And it's pretty reasonable. What happens is that there's a bunch of hyperplanes in X. Okay, right? So for instance, there's a red hyperplane dual to these 4 red one cubes, right? See that red hyperplane that I haven't drawn, but I've just drawn the 1 cube that it's dual to. Okay. Now you take all of your hyperplanes and you make a graph. Okay. There are 8 hyperplanes, and my graph has 8 vertices. And you connect 2 vertices of this graph by an edge if the corresponding hyperplanes cross each other. Okay? So that's the rag, that's the simplicial graph associated to the rag, which the fundamental group of this special cube complex lives inside of. Okay? You don't have to know anything. You don't have to know about that to follow this talk. All right? Okay. Special cube complexes. So we know what those are. Dual cube complexes. So how are we going to get from groups to cube complexes? Well, first of all, a wall space is a space together with a bunch of walls. Okay, here's each wall it's basically a partition of the space, right? The stuff on one side of the wall, stuff on the other side of the wall. Okay, but we'll just think of them as walls. And here, for example, here are some wall spaces, right? The space is this oval, for instance, in this case, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9 walls over there. They're all dotted lines. This is a very simple example because the walls don't cross each other. Okay? Here the walls are crossing each other, right? Here they can even cross each other in triples. Right? 3 of them can pairwise cross each other. It's a more complicated example. Now, there's a construction due to Sagiv in his thesis, which I'm going to talk a little more about in a moment, which says that whenever you have a wall space, it's dual to a cat-0 cube complex. Okay? And that is something that you basically are very prepared to accept. Watch. Probably this example is the one we should start with, because you're all comfortable with the idea of a tiling and the dual to that tiling. Okay? Because we all love that. Okay? So what do? You look at the one skeleton of the tiling and you kind of remove it, right? And for each region in its complement, you get a vertex, you get a 0 cube, and whenever 2 regions share a wall, then you get a 1 cube joining them, right? And whenever you have a crossing pair of walls, you'll get a 2 cube. Right? I'm just showing you what you already knew. I'm just reviewing it in this context. Now, let's go back a little bit to this picture over here, which is simpler but a little bit less familiar, and it has a dual just as well, right? The 0 cubes of this dual are the complementary components, right? And so this 0 cube and that 0 cube are adjacent. Here they are. They're adjacent to each other. Right, because those complementary components share a wall. Okay? So how do you generalize this so that it can handle more complicated wall spaces that aren't, where there's a higher a level of complexity where you can have 3 or more pairwise crossing walls? Okay? So the way to do that is, I'll just describe it very quickly so that you have some sense of the flavor over here. A 0 cube is a choice of orientation for each wall. What do I mean by that? Put a normal vector on each wall, either the normal vector pointing to this half space or the normal vector pointing to that half space. Okay? So a 0 cube is you're choosing a normal vector for each wall. Okay? So this 0 cube over here corresponds to that choice of all of those blue normal vectors for all of those walls. Okay? Except that you have 2 conditions. You don't want to have 2 normal vectors pointing away from each other, in this sense, right? Their associated half spaces have to intersect more rigorously. And the other thing's not so important for us. You don't have an infinite sequence of normal vectors all pointing away from some point. Okay? And you add a 1 cube joining 2 0 cubes if their orientations disagree on exactly one wall. So for instance, if I, let's see, so this 0 cube and that 0 cube over there, they would disagree on this wall right over here. So if I flip this normal vector, then everything would be kind of pointing towards that point over there, and you know so I'll flip this normal vector, I get to this to this 0 cube over here, and if I flip this one, I get down over there, and so forth. Okay, so to give you a little bit of a flavor. So the dual of this guy over here is like a Rubik's cube. It's a cube complex. It ends up being 3-dimensional. What ends up happening roughly is that you get an n cube whenever you have n pairwise crossing walls. And actually, I should say, once you know what the 0 skeleton and the 1 skeleton is, you just add the higher skeleton wherever you think that it exists. Okay, if you see the 1 skeleton of a 2 cube, throw it in. If you see the 1 skeleton of a 3 cube, throw in that 3 cube. Okay? Okay, so that's a dual cube complex. Now we have to give a brief introduction to geometric group theory. I'll do it standing on one leg. Okay. First of all, Cayley graphs. So if you have a group with a bunch of generators, then it's Cayley graph. You get a vertex for each element of the group, and you join 2 vertices by an edge when they differ by a generator. Okay, so there's 2 examples. Here's 2 different groups given by presentations, and here are their Cayley graphs with respect to those generators. Okay, I'm sick of drawing the usual Cayley graph for z squared, so I've done it with 3 generators over here. Okay, it was very stress reducing. Now, when you have a Cayley graph, it's a graph, so it has a nice path metric, right? To join 2 points, you just do the obvious thing. The obvious, you count up how many the minimal number of edges joining 2 vertices, for instance. Right, that's going to be a geodesic, and if points lie in the middle of edges, you could do something similar. Now, a group is hyperbolic if there exists a number delta more than 0, such that all geodesic triangles in the Cayley graph are delta thin. So whenever you take three points in the Cayley graph, right, and you look at a geodesic, 3 geodesics in the Cayley graph joining those 3 points, then each side lies in the union of the delta neighborhoods of the other 2 sides. Okay, you just think of this picture. It's delta thin. This green one lies in the delta neighborhood of those other 2 sides, which there's some fixed number delta. Okay. Now, of course, if you choose different generators, you might have to use a different delta. But actually, if for some set of generators, all geodesic triangles are delta thin, it's true that for any set of generators, for any finite set of generators, all delta triangles, for each set of, for another choice of generators, all your triangles are going to be delta prime thin, but for some other constant delta prime. Okay? Now, 2 interesting notions that you get within a word hyperbolic group. So you're treating, as Gromov taught us to do, groups as geometric objects. One of the things is that certain subgroups become favored, subgroups that have good geometry. So for instance, a subgroup is quasi-convex if it's pretty much convex. It's pretty much a convex with respect to this metric. So it's quasi-convex. So you look at this subgroup. The subgroup is a bunch of vertices in the Cayley graph. Right? Because the group is all the vertices. Subgroup is a subset of those vertices. And what you do is you look at the geodesics which start and end on the subgroup, and you want them to lie uniformly close to the subgroup. Okay? So any geodesic, your subgroup is quasi-convex. If any geodesic that starts in the Cayley graph that starts and ends on the subgroup lies in a kappa neighborhood of the subgroup. Okay, so this is the picture. Another thing that you have in a word hyperbolic group is a so-called boundary. So you start at a point, and you look at all the geodesic rays in the Cayley graph emanating from that point. And two rays are close to each other if they're traveling next to each other for a very long time. That's the way you topologize it. Okay. All right, so for a free group, its K-graph with respect to the usual two generators would have 0 thin triangles. It would be word hyperbolic. Its boundary would be a Cantor set, and in fact, all finitely generated subgroups are quasi-convex. All right, so now you all know geometric group theory.
Boundary is an equivalent class of rays.
That's correct. That's correct. I didn't explain it in full detail, but once you hear the idea, you kind of know what to do. Okay, exactly. Okay, so the boundary is an equivalence class, and then to topologize it, if they're staying next to each other for a while, you got it. Okay, so now I told you that codimension 1 subgroups are subgroups that cut the group in half, and now I'll just say it again. With some examples. Okay, so here's a cyclic subgroup inside of Z squared, right? So you're thinking of Z squared, you're thinking of its Cayley-graph, and the cyclic subgroup is some nice patterned subset in the Cayley-graph. And in what sense does it cut the group in half? Well, what you do is you take some finite neighborhood of that subgroup, and when you remove that finite neighborhood of the subgroup from the Cayley-graph, then as you can see, you kind of tear out this, little neighborhood of this set of red dots, and you get 2 infinite complementary parts, right? And that's the sort of thing that's basically what it means to be codimension 1. It's not quite an accurate definition. The accurate definition is that there'll be at least 2 H orbits of complementary components that don't lie in a finite neighborhood of the subgroup. Okay, but that's for later if anybody wants to discuss that with me. All right, what you should be thinking of is the fundamental group of a pi1 injective codimension 1 submanifold, an immersed codimension 1 submanifold. The fundamental group of a circle which is living inside of a surface, a pi1 injective immersed circle inside of a surface. Its fundamental group is going to be a codimension 1 subgroup in the surface. And if you look at the sort of universal cover of this surface, it kind of looks like the Cayley-graph. And that sequence of red dots will kind of look like the lift of the universal cover of this immersed circle, and you could see how it cuts it in half, how it cuts the universal cover in half. Well, back to Sagiv, what he did really was he took a codimension 1 subgroup as an input, and he output an action of a group on a cat 0 cube complex. And you know how to do this now. Basically, when you have that codimension 1 subgroup, so you have your Cayley-graph, right, which maybe looks something like this. Here's your Cayley-graph, and your codimension 1 subgroup is going to be some sequence of points, right? And when you take a neighborhood of it, then you get a wall, right? Especially if you're looking at it from far away, all you really see is this kind of red blur over here, right? And there's the stuff on the one side and the stuff on the other side. This is infinite, okay? So you take your wall and you translate it around. So there's one over there. So maybe I'll translate it for you. Here it is. You've got this one wall, and then you translate it by the group action, and you get another wall. You translate it again by the group action, you get another wall. And you keep on doing this, you get a whole bunch of walls. Right? And now you have a wall space. Okay? And your wall space has a dual. Okay? Well, we've already discussed. Except now the group is going to act on that dual. Okay? Because the group is acting on the wall space, it's going to act on the dual as well. All right, and I mentioned that if the wall space is if the subgroups are nice, then the group is going to act nicely on the wall space. In particular, if the subgroups are quasi-convex and the group is word hyperbolic, then the group is going to act co-compactly on the dual cat 0 cube complex. If you have many walls, if you have sufficiently many walls, then the group is going to act freely. Basically, what you should imagine is if these walls are cutting the Cayley graph up into many tiny little finite pieces, then the group is going to act freely on the dual cube complex. Okay. Okay, so now we know where our cat zero cube complexes are going to come from. Now, let's see what happened over here. If I understood that this gets complicated. Yes, it does. But we'll figure that out. 2009, I think, or 2008, Kahn and Markovich solved an amazing open problem. They showed nobody, despite huge efforts in understanding hyperbolic three manifolds, a problem that withstood everybody's scrutiny was how to show that a hyperbolic three manifold has a pi1 inject has an immersed pi1 injective surface, right? So you have the fundamental group of a hyperbolic three manifold. They wanted to know does the fundamental group of this three manifold have contain the fundamental group of a closed hyperbolic surface? Okay, and they cracked that problem and actually cracked it in a very strong sense. They showed that if you look at the universal covering of your three manifold, the universal covering of your three manifold is a very nice, well, it looks hyperbolic three space. Its boundary, right, is the boundary of the group actually. It's going to be a two-sphere, and they showed that for any circle in the boundary of hyperbolic three space, in the boundary of the universal cover of your closed three manifold, for any circle inside, there exists a surface which maps into the three manifold K, mapping into the three manifold M, so that the fundamental group of that surface is quasi-convex. It's called a quasi-Fuchsian in this context, and actually the boundary of that surface is going to closely approximate the that circle. So here's the picture over there. So there are loads and loads of surfaces. That's why it was hard for everybody, because there were just so many. Okay. Now, in fact, what we had already understood was that if you have a word hyperbolic group and it has the following property, let's see. So you have a word hyperbolic group and you look at it acting on its boundary. So this is the boundary of your word hyperbolic group. And if it's true that for any 2 points, P and Q, you could find a quasi-convex codimension 1 subgroup whose boundary separates P and Q. Okay. So for any 2 points in the boundary, you can find find a subgroup whose boundary separates those 2 points, and you can be thinking of a Sierpinski carpet is the boundary of your group, and the subgroup is maybe a Cantor set. It's a free group, and its boundary is a Cantor set living inside. It's hard to see it, but it really is a Cantor set. So if your group has this wonderful property that points on its boundary are separated by boundaries of quasi-convex codimension 1 subgroups, then actually you can find subgroups so that the group will act properly and co-compactly on a cat-zero cube complex. Okay, so the upshot is that because of Kahn and Markovich's amazing achievement, any hyperbolic three manifold actually acts freely and co-compactly in a cat-zero cube complex. That cat-zero cube complex, it might be 17-dimensional, or much, much worse than that, right? But it is going to be a compact cat-zero cube complex with the same homotopy type as your original closed hyperbolic manifold. Okay, so at around the same time, I was trying to understand which cube complex and which cube complexes are virtually special. I was trying to understand which groups are special, and this is actually sort of almost doable. Let's see. A group has a hierarchy if you can build it up using amalgamated free products. If you can build it using amalgamated free products and H&N extensions. Okay, these are just generalizations of free products. And you should just be thinking of this example over here. So if you take a surface, you can keep on cutting a surface up along pi1 injective subspaces. Right? So here I cut it along a circle, I get these two surfaces, and then each of these let's see, if I cut this surface along that blue circle, I'll get this surface over here. And then if I cut that surface along the green line segment, I'll get this surface over here. And if I cut along the purplish line segment, I'll get this. And this is just a disk. Its fundamental group is trivial. Okay? And this sequence of cutting the surface up into pieces until you get something which is contractible is mirrored on the group theory level. You're cutting up the fundamental group of this surface along subgroups until you get trivial groups. That's basically what a hierarchy is. And if whenever you're cutting, if you're always cutting along quasi-convex subgroups, that's what I call a quasi-convex hierarchy. So, all right. Basically, what I showed was that if a group is hyperbolic and has a quasi-convex hierarchy, then the group is virtually special. So certain hyperbolic groups are actually virtually, meaning they have finite index subgroups with the property that they live inside of rags. Okay? So the requirement is that C should be quasi-convex. Okay, so the group is hyperbolic. We require that you're not cutting along crazy subgroups. You're cutting along subgroups that are almost convex. Okay, and well, this had my intended application was to three manifolds. That's the problem I was after. So in particular, if you took a hyperbolic three manifold with cusps, then this theorem, or something slightly stronger than it that I didn't mention, was already powerful enough to show that if you have a hyperbolic three manifold with cusps, then the fundamental group of that three manifold is virtually special. So a hyperbolic knot complement, for example, this theorem is powerful enough to show that hyperbolic knot complement has fundamental group which is virtually inside of a rag. Right? Another consequence was that a one-related group with torsion, if you take a one-related group and you just make it a one-related group with torsion, meaning that the relator is a proper power, then that group is residually finite, which means that every non-trivial element survives in a finite quotient. Okay, these are, it's not at all clear that these two are related to each other, but they're both very closely related because in both cases, the groups have hierarchies or have subgroups of finite index with hierarchies. Okay.
Could you understand the definition of quasi-convex?
I can. It didn't occur to me that anybody was still following me at this point. Okay? So you're a little bit surprised now, not sure what to say. Here's what quasi-convex was, right? So you have the Cayley graph, you have a subgroup, it's a bunch of vertices in the Cayley graph. And to be quasi-convex means that the subgroup is almost straight, it's almost flat inside of the whole group. Any geodesic in the Cayley graph that starts and ends on the subgroup.
This applies to subgroups H which divide. So the ball in hyperbolic space would not be quasi-convex at all. The ball, the sphere. What is not quasi-convex at all?
Well,
Points.
That's right. Yeah, that's right.
So this applies to these subgroups H, which somehow.
So the Kahn-Markovich subgroups are, if you look at this, imagine this as the universal cover of a surface, right, which is immersed inside of your three manifold. I'm drawing with a laser, but you've got a surface which is living inside of your manifold, right? And I'm looking at the universal cover of the manifold. That's that picture over there. And the universal cover of my surface, K tilde, is living inside, and it's just a little bit wiggly. It's pretty much straight. It almost looks like a codimension 1 hyperplane. Okay? And so it's legitimate. Okay? It is quasi-convex. Okay. Huh? But it isn't so crazy after all. It's a little bit wiggly, but it's coarsely the same thing as an actual circle, as a genuine circle. We can fight about it afterwards in a minute or two. Yeah?
Today, Kahn-Markovich, this is, say, our understanding that as approved, that it's an easy track now, or it's...
My understanding has not... No. It's not my topic, and I haven't studied it. My understanding of it has not improved since 2009. But other people who, the next generation that comes in, what always happens is what was really, really tough for previous people gradually becomes, first of all, not so surprising. How to do it? Oh, yeah, we always thought we would do it that way. We'll eventually feel that way. So that's the way it goes. Let me now finish my thoughts, though, okay, and then we could talk about it. This I can spare you, except to tell you that to prove this theorem, I had to work hard. It involves a whole bunch of crazy ingredients it's several hundred pages of effort and a lot of sweat. So I'll mention one, but I'll spare you for that. I'll mention one ingredient over here, which turns out to be surprising and rather central in this whole business. And to make it as simple as possible, I will lie to you completely about its statement. Okay? You have a group that's special, right? What does that mean? It means it's just a subgroup of a RAG. Okay? You take a subgroup of the group, H, and you quotient by the normal closure of that subgroup. And the result is again special. That's the special quotient theorem. So you have a group, you have a subgroup you don't like, you kill that subgroup, you're again special. Okay, you can kill subgroups of special groups and you're still special. Okay, that's a lie. And I have some gradually, in fact, you have to kill a finite index subgroup of your subgroup. You can't kill the whole subgroup. And the result is not going to be special. It's just going to have a finite index subgroup, which is special. But this is now, draw you into my world over here. I know, because when I was first telling people about this, told all my friends about this, all crazy excited about this, their eyes were totally glossed over and they didn't know what I was talking about. Okay? So I realized that the actual statement is a little bit difficult. So you have to assume your group is hyperbolic, that it's the fundamental group of a compact special cube complex, and you can kill given a finite quasi-convex subgroup, you can kill a finite index subgroup of it so that you get something which is again virtually compact special. Okay, and I put one example over here. We could duck that. The conclusion, though, shortly after, a couple of years after I did this, building on my work, Ian Agel was able to, attain what was my ultimate dream over here, which was if you have a compact, non-positively curved cube complex whose fundamental group is hyperbolic, then that cube complex X has a finite cover which is special. Okay, and what that sort of clears up a whole bunch of things. It's really an amazing result, and resolves problems about hyperbolic three manifolds that we knew from my work that this was going to be the way it goes. That they're virtual Hawken problem and virtual fibering, also the virtually infinite first Betti number and so forth. But another conclusion that you might not have heard of. Another conclusion that you might not have heard of is that if you take a random group, if you take a 3-generator group, 7 relators chosen at random, then that group is residually finite. Any element survives in a finite quotient. Any non-trivial element is going to survive in a finite quotient. Because that group is linear. That group is virtually special, actually. And it's because, a random group of this type is going to, can be cubulated using, the scheme that we discussed, and then it's virtually special because of this theorem. So, let's see. This is just what we started with, right? So, in our case of interest, right, we had a hyperbolic 3-manifold. Kahn and Markovich find us a bunch of codimension 1 subgroups. Using Sagiv's construction, we get a cat 0 cube complex that is dual to those surface subgroups. And then Ian Agel tells us how to pass to a finite cover of the cube complex with the same homotopy type of that 3-manifold, so that it is special, and then we know once it's special that we can send it into a RAG. So it's a strange conclusion that we have, which is that many groups that we're all very that we've been very fascinated with in geometry topology are turning out to be virtually subgroups of silly groups, subgroups of groups which are just RAGs, subgroups of RAGs. So thank you very much. I'm sorry I went over time.
I've been used to it. Any questions?
It's understanding a group, it's understanding a manifold and similar to understanding a group.
Sometimes understanding the manifold is understanding its homotopy type, right? So for aspherical manifolds, the homotopy type is determined by its fundamental group. So partially yes. Many properties of manifolds, certainly in 3 dimensions, are very strongly represented by properties of their fundamental groups, and not always.
Suppose you wanted to do this the group in terms of this. You are bringing manifolds in, so arguably, quite to see what extent the copy will groups and what extent the copy will locally.
No, there are no manifolds. There are no manifolds here except maybe even this part. I suspect, and I now have more increasing evidence. Even that part is entirely just groups, and there's very little manifold going on over here.
Is that because the manifold is more difficult?
No, it's because the types of questions that we would ask about the manifolds can be formulated just in terms of the group theory. Okay, for those types of manifolds. I mean, that's typical for hyperbolic manifolds. It's the group theory controls a lot of the stuff for certain types of questions, right? For questions which are very geometric, spectral questions about the shape of the manifold or whatever, you wouldn't be at all interested in anything that I'm saying, because I pass through finite covers and you ruin the geometry. But yeah.
Are higher dimensional hyperbolic manifold groups expected to have lots of codimensional?
Yes. Please figure it out. This is what. So I believe that this scheme will work for all closed hyperbolic manifolds. Yes, and there are for the arithmetic ones. The answer is that we know it for 3/4 of cases that it already is known to work. So, I'm sorry. For rank 1, for the hyperbolic rank 1. So for higher rank, this fails very much. Thank you. For SL3Z, for SLNZ, where n is large, total failure. You've heard of Kashtan's property T. Kashtan's property T does not allow codimension 1 subgroups, and so SL3Z, this scheme will not give us any insight into that group, unfortunately. So for higher rank, guys, forget it. But for hyperbolic manifolds, this is what it looks like. The generalization of Kahn and Markovich to high dimensions doesn't exist. Nobody knows how to do that, right? So we stop.
At this point, I'd like to present the audience with a couple of alternatives. I want to mention that the geometry seminar in the University of
Toronto kindly shifted their with this one, and they were still scheduling that. There's an opportunity to have some refreshments, perhaps before you want to start your talk. Take a few minutes for that, and of course to discuss with Professor Wise. And I'd like just to finally 2 things to present you. So, Danny, please just step here forward just for one moment. First of all,
Portion of the prize.
Okay, thank you very much.
The CRM-Fields-PIMS prize. And then this is purely an honorific thing, but this is a plaque awarding you as a Fields Institute Fellow.
Okay.
Which
It's good that I'm not a woman. Then I'd be a gal of the Fields Institute.
no, they're all fellows.
Okay. All right.
But
Well,
it will last
thank
longer
you.
than the prize.
Thank you. It will outlast me, I'm afraid.
And thank you so much for coming.
Thank you.
And presenting this beautiful lecture.
Okay. Thank you. Thank you. Thank you. Okay.